Next, we talk about subtracting. If you think subtracting is the same as adding, you are correct. It's just a matter of subtraction in between. So think about it just like we did when we were practicing one of our weeklies where we had like things like 2x and minus 7 or something like that. And then we were subtracting a whole other polynomial, 3x minus, I don't know, 4. I don't want to put too many of the same numbers because then they all start getting wacky. Think about this subtraction distributing to each of the things in the second matrix. Okay, that same thing happens. So we actually don't have a minus and a 3x and a minus 4. We have a negative 3x or subtracting 3 more x's. But then I have a minus 4, and a minus can build a plus. All right, so we don't actually have a negative 4 going on here. We actually have a positive 4. That's going to change our answer because when we have a 2x and a minus 7, and then when we start combining like terms, 2x and a negative 3x, I have more negatives. I have, in fact, one more negative than I have positives. If I have a negative 7 and I'm adding 4, I end up with negative 3. So please watch your subtraction. Yes, distribute your subtraction. It does the same kind of thing. So if I want to find matrix A, I'm subtracting matrix B. We can set it up in that same way where I'm going to subtract corresponding elements. I'm going to have a 4 minus 7 as my first element. 4 subtract 7. Well, 4 minus 7 is a negative 3. I'm going to go ahead and kind of start building my answer matrix here as long as I'm using the same colors. In row 1, column 2, I have 8 minus a negative 9. 8 minus negative 9 minus negative builds a positive. So I end up with 8 plus 9, and that would be 17. Looking at our second row, first column, our first element, I have a negative 2, and I'm doing subtraction, and I'm subtracting 4. I have a negative 2, I'm subtracting 4 more, so I'm going to have an even bigger negative than either one alone. I would have a negative 6. And last but not least, 0 minus 5 leaves us with a negative 5. Once again, hit pause on that video. Let's see if you... Ooh, yipes. Sorry. Got a little carried away there. Let's see if you arrive at the correct answer with our second practice of subtraction. Again, they have to have the same dimensions. These ones do. 2 rows, 3 columns, 2 rows, 3 columns. Same dimensions, good to go. Try this practice. Hit pause. See if you get the right answer. I'm only going to give you the first 2 columns of answers. You have to finish the third column. Alright, so there's 2 out of the 3 column answers. So remember, 6 minus a negative 4 is going to build a plus. 6 plus 4 is that 10. Negative 9 minus 3 more. We're going to subtract 3 more numbers from that. That's a negative 12. So make sure you are continuing on with that pattern. You do the last column. Last but not least, we're going to continue on to page 5. Because then we do this thing called scalar multiplication. When we multiply a matrix by a scalar, just like that word sounds like scale. We're adding a scale to something. And when I think about scale, I think about like scale models, right? So you can have like this big, awesome, nice car. I'm going to draw, I don't know, a VW Bug because they're one of the easiest cars to draw, right? Because they go whoop, and then they get that nice big window, and then they kind of control it. It's an interesting car. Wow, that's a sad looking car. If you have a big giant VW Bug and you like it so much you want to make a tiny scale model to keep in your house, or you want to give one to like your kid for Christmas, like a Matchbox car, they talk about Matchbox cars are scale models of the real thing. And they try their very best to meet every single dimension in the same way. So you can put something at like half scale. That looks like that might be half scale. Let's take all of that together. It's, half as long as the original, and it's half as tall as the original. So this is half as big. It's a half scale. It's like multiplying every measurement up here by half, or 0.5, and that would be our measurement for our scale model. Scalar is the same thing. It's just a number that's going to multiply a matrix, and what it does, just like what we saw before, it is actually going to apply to every single element inside that matrix. The same measurement I have up and down here is going to apply to this measurement up and down here. Each and every single element, the total height of the car and the total height of the model. The scalar product is the product, the result, the answer, when you multiply that scalar with each element inside the matrix. And scalar multiplication is performed by multiplying a number by each element of a matrix. We're going to start seeing how we do some of that stuff. Oop, hang on, I have a timer going off. Okay, I'm back. My daughter's cookies. She's playing with her Easy Bake Oven right now, so her cookies are done. But she's outside playing in the rain. So, there's that. So a scalar. A scalar can make something bigger, and it can make something smaller, and it can turn something negative, or it can turn something positive. It can do all the same things that multiplication does. If we multiply by a big number, if we multiply 10 by 4, it gets even bigger than 10 started with. It gets 4 times bigger, and it gets to 40. If we multiply it by a half, it's going to be smaller, half the size. So 10 times 1/2 is 5. It's half of 10. And we can even multiply it by a negative. We can do all the same things with matrices. So I ask you two things. I ask you to take this matrix A and multiply it by 2. And when we do that, it looks like this, 2 times matrix A. So the big capital letter, I want to remind you, big capital letter means an entire matrix, not just one value. So matrix A is 1, 2, 3, 4. Here's my matrix A, 1, 2, 3, 4. And to multiply it by a scalar of 2, we're just going to distribute that 2 to everything inside of it. 2 times 1, 2 times 2, 2 times 3, 2 times 4. And of course, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8. So we get this nice nifty answer matrix here. On our second example, our second thing I asked you to find, or as an example up here, is negative 1a. So I'm simply going to show it like this, negative 1a. That means negative 1 multiplies everything inside. Negative 1 times 2 turns it negative 2. Negative 1 times 3 means negative 3. Negative 1 times 4, negative 4. Scalar multiplication, pretty straightforward. I really like this one a lot. So I've got a couple examples for you here. I'm going to do, I think, the first one and the last one. I'll leave that middle one for you to do on your own. Only because students start freaking out again with the fractions. We don't have to get scared of fractions. All right. So I'm taking 2/5 of everything in A. So I need 2/5 times 20. And be careful typing this in your calculator, because your calculator, if you just type it in as 2 divided by 5 times 20, it may not know exactly what order you're working in. So if you want to, you could just, put that fraction in parentheses, 2/5 times 20. Or you could do it like I do. 2 times 20 is 40, and 40 divided by 5 is 8. And there we go. There's our first answer. Looks like I'm going to have a 2 by 5 matrix. That's an interesting one. Alright, so now I need 2/5 times 2. There's the second element. 2 times 2 is 4 divided by 5 is going to be a fraction, so I'm just going to leave it as a fraction. 2 times 2 is 4. Divide that by 5, it's 4/5. Next, let's do this mamma jamma. 2/5 times 35. Well, let's see, 2 times 35 is double 35. That is 70. 70 divided by 5. Let's see, 7 divided by 5, it goes in one time. Sorry, and 20, that's 2 left over. 20, so that'd be 14. Some of you may have grabbed your calculator on that one, that's fair. 1 times 2/5, well, anything times 1 is itself, so 2/5 times 1 is the same as 2/5. And last but not least, in this row, 2 times 2, well, wait a second, I already did 2 times 2/5. I already did it right there, so I'm going to get the same answer, 4/5. Oh, we're halfway done. Just one more row to go. -5. I'm sorry, 2/5. 2/5 times -5. Well, let's see, 2 times -5 is -10. -10 divided by +5. Negative divided by positive is negative. 10 divided by 5 is 2. 2/5 times 6. 2 times 6 is 12. 12 does not divide by 5 evenly, so I'm just going to leave it as a fraction. 12/5. Sorry, that's kind of in the way. 10. 2/5 of 10. 2 times 10 is 20. 20 divided by 5 is 4. We're rocking and rolling. 2/5 times 3. 2 times 3 is 6. 6 does not divide by 5 evenly, so I get 6/5. And last but not least, 8. 2/5 times 8. 2 times 8, 8 and 8 is 16. Doesn't divide by 5 evenly, so let's just leave it as a fraction. 16 divided by 5. Now, if you did put those in decimals, it would be correct. There's nothing wrong with that. Decimals are a-okay. So if you have, sorry, I'm just making sure that this is clear, that it's a negative 16 over 5, not over -5. There we go. Kind of did that backwards. So if you put these as decimals, it's okay to have something like 0.8 instead of 4/5. It's okay to have something like 0.4 instead of 2/5. It's okay to have 1.2 instead of 6/5. So if you have them as decimals, that's okay, but please do make sure that they are nice rows and columns, and you've got your brackets on the outside. Now, as I said, I was going to skip with this one, but make sure you take that negative, multiply everything by a -4. Last but not least, if we have a matrix below, it shows population of a school separated by gender for grades 4, 5, and 6. So this tells me this is 4th grade, and 5th grade, and 6th grade. And I don't know which one's boys or girls because I didn't feel the need to label them for us, but that's okay. What would the populations be for each in a school 3 times the size? Well, there's our clue right there, 3 times. And so that means I want this whole matrix times 3. So we're scaling it up as if we were 3 times the size. So I'm going to take each and every single number. I'm going to multiply it by 3. Yeah, I'm firing up the calculator for this one. So I'm going to just take each number, multiply it by 3, and then I'm going to put my answer into a final matrix. I'm going to need a 3 by 2 matrix. Our matrix after a scalar should be the same size as what we started with. Why isn't it launching? Where's my calculator? Although really for this one I don't need a fancy dancy calculator, I just need a quick one like this. So here we go, 45 times 3, 135. 39 times 3, 117. This is all we're doing. We're just taking each number and making it 3 times the size. Lots of times, cities and schools and states will do this when they're trying to figure out how many they estimate a group is going to grow by. So if they know that they're getting twice as many kindergartners registering, or students registering for kindergarten as they did 2 years ago, they can take the numbers of students from 2 years ago and multiply it by 2. If they're getting twice as many students registering, they can multiply it by 2, and then they have a really great estimate of how many they're going to need, how many students they can expect to have enroll this year. Last but not least, 45 times 3. Oh wait, I already did that one. That was the first one too. So same number, let's be efficient. And let's just do it like this. We have our nice solution if that school were 3 times the size. Make sure you have this one finished. Go ahead, take some time, do it right now. Just multiply every element by -4 and write down your answer in a nice series of a 5 by 2 matrix. Thanks for watching. Make sure you have picked up this organizing data worksheet, and whatever you don't finish here in class, please finish at home. If you finish early, flip over to the back side. Start working on that. I'm sure you're going to do just fine. Hey, I'm looking forward to seeing you guys. Happy Pi Day. Give your friends a 3.14 instead of a high 5. Give them a high 3.14. I'll see you guys soon. Thanks. Bye.